Hello, Quest. Okay, so I want to kind of go over that exact same problem as before, because that, took a lot of work. But I wound up erasing the whole thing because I'm going to need quite a bit of space on the board. So right now I lift up that formula. I'm going to erase it if needed. But the idea is, let's look at a general problem. Where we just have two materials, say lengths L1 and L2, and their conductivities K1 and K2. And we want to kind of just come up with a formula where we can do this at once without doing multiple steps where we have to find this boundary temperature. But just like before, we have TH and TC for hot and cold, and TB is the boundary. We'll say this is P1, the rate that energy flows through material 1. P2 is the rate material flows through material 2. And these two have to be equal to each other. So we're going to try and do this all algebraically and come up with a nice formula in the end. So to start with, P1 equals P2. So what I'm going to do, for now, I'm going to put this K back on top. So we have K1A times delta T for material 1. That'd be TH minus TB. And that would be divided by L1. And then for P2, we have K2A. Delta T in this case is TB minus TC. And then we divide by L2. So we can cross off the A. And let's multiply by L1, L2. So we have K1 times L2. I'm actually going to distribute this. So we have this times TH minus TB. And we multiply by L1, L2, so the L1 canceled out. So we have K1, L2. And then that equals, similarly, L2 is going to cancel out. We'll have L1, K2 times TB minus TC. So this would be TB minus L1, K2, TC. And now we want to solve for the boundary temperature. So we're basically just doing with variables what we were doing with numbers before. And then we're going to plug that back into the formula. And we'll have a formula that does not involve this boundary temperature at all. We plugged it back in. So we get something that just depends on the L values and K values. I just realized that should be an L2. K1, K2, and the hot and cold temperatures at the two ends. So let's solve for TB to start with. Let's move this term over here and this term over here. So I'm going to write the terms with TB on this side. But here we have L1, K2. And then we move this one over, so we'd have plus L2, K1. So those are the two terms. Here we have TB, we have L1, K2, and K1, L2. And we factor TB out of it. And those were over on this side. So on the other side, we have K1, L2 times TH plus L1, K2 times TC. So what I'm going to do, I want to try and save space. For now, I'm going to define something called S, just for sum. That'll be L1, K2 plus L2, K1. And so we have TB times S equals this. And so we'll write the boundary temperature here. So we have, I'm going to write it L1, K2 Actually, let's do it this way. We'll just do it the order it is. We have L2K1 times TH plus L1K2 TC, that whole thing divided by S. So, yeah, then I'm going to erase things and try to leave enough board space. So, again, there's a lot of steps involved, so I would like to, one mistake anywhere can screw everything up. So what I'm going to do is check everything, make sure it's right, and then we can move on. So I start with K1A over L1. That looks good. That looks good. So K1 L2 TH minus TB. That looks good. This one should be L1 K2 times TB minus TC. So L1 K2 plus L2 K1. That looks good. Oh, I think I did make a mistake somewhere. So I move this term over here, factor out the TB, that's good. And then over on this side, we have L1 K2 times T, oh no, that's right. And then K1 L2 TH. So I think this all looks good. And we have this boundary temperature TB. I'm just going to make sure I wrote that down right, and then we'll move on. L2 K1 TH, L1 K2 TC over S. Okay, everything's looking good so far. So I'm going to erase everything now. I'll leave the picture if we can. But let's just calculate, say, P1. So here we have K1A times delta T. I'm going to write it, I'll distribute. I think we'll try it like this. So we have P1. We'll move the K on top for now. We have K1A over L1. That's these, and then TH minus TB. So now we want to plug in TB, and this is where things are going to get kind of messy. You know what? I'm going to redraw this over here. Not that we really need it, maybe, but okay, so let's erase this just to make sure that that won't get in the way. So now we're good here. Everything here is fine. It's this part, we have to get rid of the TB, so we're going to plug that in. So actually what I'm going to do is I'm going to multiply the numerator and denominator here by S. So we have K1 A S TH over L1, times S, and then minus K1A over L1 times TB, which is this kind of mess. Okay, so now our denominator is the same. And maybe we can wondering, maybe let's multiply, so the denominator is L1 times S. So let's for now say L1S times P1. See if we can clean up this right side. We have K1 A S times TH. Let's do that. We'll do maybe one step at a time. And then minus K1A L2 K1TH. And then we're going to subtract this term, so we have minus K1A times L1 K2 TC. I think that's, let me just double check that. So yeah, we got rid of the denominator by multiplying both sides by L1 times S. So first term, K1ASTH. Second term, we have K1AL2 times K1 times TH. And then minus, so that would be minus K1A times L1 K2 TC. So in a sense, it's almost like we're done. We don't have, we could just plug in everything because we got rid of TB. So in this problem, we know L1, we know S because, that involves L and K's, which we know. We know the area. We basically know everything here, but what we want to do is really clean this up a lot. So let's factor out a TH on this side. So we have TH times, every term involves an A. So let's divide that out. Okay, so we have T1, TH, we'll factor that out. And then the first term we have K1 times S. So we have L1, K1, K2. So we're multiplying S by K1. So L1, K1, K2 plus K1 squared L2. So, K1 times S. That should just be these two terms. So that's gone for a minute. We factored that out. So yeah, L1, K1, K2 plus L2, K1 squared. So the A we divided out. So we have K1 times S times TH. But then we want to subtract this term, which is minus K1 squared L2. And then we have minus K1, or here, let's do this. Minus L1, K1, K2 times TC. And something really nice happens here. These two terms cancel out. They're both K1 squared L2. So that was nice. And now we can write this L1. We still have this annoying S in here. But we're getting somewhere now. Here we have L1, K1, K2 times TH, and then L1, K2, K2 times TC. We can factor that out. L1, K1, K2 times TH minus TC. Okay, so we're getting there. We want to solve for P1, so let's do that. So P1 is A. We've got that. Oh, we can cancel out the L1. That worked out nicely. So what we have is A over S times K1, K2. I'm just going to call it delta T for now. delta T is TH minus TC. So we cancel out the L1. So P1 is A K1 K2 over S times delta T. So off to the side, I'm going to have to erase a little bit to make room for this. Let's calculate K1 K2 over S. So I'm going to erase all of this. You can think about a recording, so you can always go back and watch it again. So let's get rid of this. Okay, so let's just look at K1, K2 over S. That would be K1, K2 divided by L1, K1, or L1, K2, sorry, plus L2, K1. And let's multiply both sides by 1 over K1, K2. So what we have on top, we just have 1. K1 over K2 times 1 over K1 times K2, they cancel out. And so what we have here, if we distribute this, we'll have L1 K2 divided by, the K2 cancels out. So we have L1 over K1. And then the second term, we have L2, and then K1 over K1, K2. And the K1 cancels out. So finally, we can write our answer. So we have A delta T and then times K1, K2 over S, which is this. So we have 1 on top, so then we have L1 over K1 plus L2 over K2. And this is kind of our final form. However, let's write this down and move on. So I'm going to put this picture back here. I'm going to write it like we had it before. We're going to have the same numbers as before. I think this was L1 and this was L2, where L1 was 19 millimeters. L2 was 76 millimeters. K1 was 0.08 watts per meter Celsius degree. K2 is 0.03 watts per meter Celsius degree. And delta T is 21 Celsius degrees. We had 25 and 4. So let me just double check these numbers. And so now with this formula here, we can calculate, in kind of just one step now. Let me rewrite this formula here. Okay, so let's get rid of everything we can. We don't need this picture. Don't really need any of this anymore. Yeah, so it's kind of an algebraic mess working this out. But the good news is we only have to work it out once, and then we can use it whenever we like. So let me just double check these numbers again. So the wall is 1, that's 19 millimeters, got that. Insulation is 76 millimeters. The insulation is 0.08. The insulation was, oh wait, let's see. Let me just reread this. oh no, the insulation was 0.03, so that should be K2. Yeah, K1 is the wall itself, that's point. Oh yeah, we also had the area. .35 meters squared. Roughly a 6 by 6 wall, not that big. And I'm going to write down the answers that we had. Well, actually, here, time is 3,600 seconds. I'm only going to write down the answer that we had with the insulation. That was 9.5 times 10 to the 5th joules. And so we want to check this formula, see if we can just do things directly, and we should get the same answer. So let's do this. So we have, let's do this. Let's do L1 over K1. So we have 19 millimeters. I'm going to do it like this. So we can say that's 19 meters divided by 1,000. And then K1 is 0.08 watts per meter squared. Or watts per meter Celsius degree. So 0.08 on the bottom. You multiply by 100 over 100. 100 on top, 8 on the bottom. Okay, so what we get here basically this is 19 over 80. 100 over 1,000. Yeah, we get 10 on the bottom. So let's see, 19 divided by 80. Is 0.2375. And the units are meters squared, Celsius degrees over watts. Yeah, no, it's good. Now let's do this next term. L2 over K2. So L2 is 76. We'll convert that to meters by dividing by 1,000. K2 is 0.03, so I'm going to multiply by 100. So here we have basically 76 divided by 30. So we're about 2.4, 2.5. Let's see. 76 divided by 30. 2.53. And then it's meters squared, Celsius degrees over watts. So the denominator, we just add these up. So anyways, let's look at the power. We have 35 meters squared. Delta T is 21 Celsius degrees. And then we're dividing by the sum of these two. So 2.53, and let's say that's 0.24 if we round off. So that would be 2.77. And the units here are meters squared Celsius degrees per watt. Now we're calculating power. So once we're done with this, we'll multiply by 3,600 to get the amount of heat. So the units are going to work out. Meters squared gone, Celsius degrees gone. So let's just do this number then. We'll get watts. We have 35 times 21 divided by 2.77. So it's about 265.3 watts. And now after 1 hour, if energy is flowing through the wall at this rate, if we multiply by 3,600, I'm getting 955,234. So yeah, that is 9.8 well, I'm getting 9.6 times 10 to the 5th power. So, yeah, that little 0.1 off, that's a rounding error. But we're essentially getting the same thing. And so having this formula here is very nice. Because we can just do it in one step instead of finding that intermediate temperature at the boundary. But there's another advantage to writing it this way. There's a way we can kind of simplify this. We define R to be L over K. So basically our power formula, we have A delta T over R. Now, what if we added like a third material here? Now, we're not going to work out the algebra. It was bad enough with 2. But we could, the general formula for the power, we have A times, I'll write it how it is in the book, TH minus TC in the bottom, instead of like, for one, if you just have one material, the bottom is just L over K, or R if you like. If you have 2 materials, you'd have L1 over K1 plus L2 over K2. For 3 materials, you just have 3 terms. Or another way of writing this is A times TH minus TC over sigma R. So you just, like, each material has like a length and a thermal conductivity, and you can define R as just a property of this material. So we're assuming the same area throughout, but like each material has this R value that depends on its length and the thermal conductivity. And then however many materials we have, we just add up all those R values for the denominator. So it's a very compact formula here. And it makes things a lot easier if you kind of just have a bunch of materials put together and you want to find the rate that energy is going to flow through it. Instead of having to find the temperatures at all these intermediate boundaries, we have one formula where we can just plug it in and get what we need. So that is a huge advantage in writing it that way. And we checked it, and it worked for the situation that we had already calculated. Again, I wouldn't want to go through the algebra, but the formula is good no matter how many terms that you have. I imagine maybe the formula, I haven't worked it out actually. It's one of those things that, like, someday I'll do this, but it's just an algebraic mess. But I think what would happen, maybe it's actually not that bad, because the power through each of these pieces is the same. So maybe we could just consider this a single material and apply the same formula to, so I think they just did it for 2 and then realized that you could kind of treat those 2 materials as one with an R value equal to R1 plus R2, and then apply the same formula again. And so it worked for any number of materials. So, because that part's going to factor out. Again, I'd like to work out the algebra before stating that for sure, but I think that's probably how they did it. Okay, so that'll be it for this video. And we're going to talk a little bit more about conduction in the next video.